Okay, so let's just give a couple of examples. The first example is the one that we did last time very laboriously. If you take the function capital F of x, which happens to be x cubed over 3, then if you differentiate it, you get, well, the factor of 3 cancels, so you get x squared. That's the derivative. And so by the fundamental theorem, so this implies, by the fundamental theorem, that the integral from, say, a to b of x cubed over, x squared dx, that's the derivative here. This is the function we're going to use as f of x here, is equal to this function here, f of b minus f of a, that's here, this function here. So that's, right, f of b minus f of a. And that's equal to b cubed over 3 minus a cubed over 3. Now, in this new notation, we usually don't have all of these letters. All we write is the following. We write the integral from a to b. And I'm going to do the case 0 to b because that was the one that we actually did last time. So I'm going to set a equals 0 here. And then the problem we were faced last time was this. And as I said, we did it very laboriously. But now you can see that we can do it in 10 seconds, let's say. Well, the antiderivative of this is x cubed over 3. I'm going to evaluate it at 0 and at b and subtract. So that's going to be b cubed over 3 minus 0 cubed over 3, which of course is b cubed over 3. And that's the end. That's the answer. So this is a lot faster than yesterday. I hope you'll agree. And we can dispense with those elaborate computations, although there's a conceptual reason, a very important one, for understanding the procedure that we went through, because eventually you're going to be using integrals and these quick ways of doing things to solve problems like finding the volumes of pyramids. In other words, we're going to reverse the process. And so we need to understand the connection between the two.